Okay, here's where things get a little weird. If you don't track what's going on in this video and kind of moving into the next video, it's okay. There's going to be a really clear practical application of this stuff and a skill that you can in fact accomplish. But we're going to continue looking at electrons, and we're going to look at why or what's some of the experimental evidence that electrons are just weird things. Again, there are two types of things in the universe, matter and energy. Matter typically comes in the form of particles. Energy typically comes in the form of waves. So waves and particles are two fundamentally different things that have different properties and that are measured in a different way. So if you look at this kind of compare and contrast situation here, waves spread out or diffuse across space. They can bend or diffract around obstacles, which is why if there is a light in a room and you are standing in a dark hallway, the beam of light coming out of the room is wider than the doorway because the light is bending around the edges of that obstacle. Two or more waves can overlap in space. Again, waves are typically energy, and we generally measure wavelength and frequency of the waves as their primary property. Particles, on the other hand, exist in a single point in space. They have linear trajectories. They don't spread out. They're at one place at 1 second and another place another second if they have a velocity. They move through space and have particular positions at given times. Whereas a wave, wherever it starts from, can move across large regions of space. Again, think about light filling up a room. Particles cannot overlap in space. Particles are a form of matter. And so when we measure matter, we measure masses and volumes. Fundamentally different things. Again, one of the big distinctions between waves and particles, waves can overlap. So when you see rain hitting a pond or two rocks thrown in a pond, and we can see those ripple patterns overlap, occupy the same space, move through one another. If you look on the right side of the slide and you've got the two rocks heading in the same direction, when those two arrows meet, when those rocks hit the same place, well, they're never going to actually get to the same place. Before they get to that final position, they're going to bump into each other, and it's going to change their trajectories. They're going to end up going somewhere else because those rocks cannot overlap and be in the same space at the same time. So fundamental distinctions between waves and particles. One of the kind of classic experimental particle wave distinctions is called slit diffraction experiments. And so we start with what's called a single slit diffraction. So what you have is you have some barrier with a small slit in it. Behind that barrier, you have a screen. And what you're going to do is shine a light on the slit, and you're going to look at the pattern on the screen. If you have waves and you shine waves of light, which are electromagnetic radiation, at a single slit diffraction, what you get on the screen is a projection of a path of light slightly bigger than the slit in your diffraction grating or your what you're shining the light on. Again, because light is going to bend around those edges, and you're going to get the same shape, but it'll be a little bit bigger. Now, a strange thing happens if you do what's called a double slit diffraction experiment. And there are certain measurements you have to have for how wide the slits are. They have to be roughly close to whatever the wavelengths of light are. The difference in distance between the two slits has to be a certain degree. But if you have the right setup, you'll get this diffraction pattern, which instead of showing two bars of light on your screen, it's going to show this series of light, dark, light, dark, light, dark, light, dark. Essentially what's happening here. So if we look at this picture, what we have is we have light going through a single slit diffraction. So We have that light wave, what we refer to as propagating across the screen, and then it hits a double slit barrier, and so you get two beams of light start coming through that double slit barrier, and eventually those two beams of light, just like the ripples in the pond, are going to start to overlap one another. We can see this. These are pictures of laser light going through a diffraction grating. So single slit, you get the wide band. Double slit, you get the light, dark, light, dark, light, dark. What's going on with that light, dark is what's called wave interference. So this is a picture of what's, or depicting what is typically referred to as a wave table. You actually have just a flat tray of water, and you have on the left side of this thing a motor wall, which will kind of compress and relax and compress and relax and create waves of water. So the white lines would represent the crests of the waves, the high point. Low lines would represent the space in between the lines would represent the low point or the trough. And then you hit this barrier where there are two openings. So those waves are going to then ripple through those two openings and create two different wave patterns that are going to start to overlap. Where they overlap, crest and crest, where the white lines overlap on the right side of that screen, you get what's called constructive interference. And so the highs get higher, the lows get lower. Where you have spaces between the two waves is where we would have peak of one wave and crest of another wave overlapping, and that results in destructive interference. And so you end up then with areas of, going back to this slide, areas of constructive interference, which are going to give you bright light, and areas of destructive interference, which are going to give you dark on the screen. But this represents a wave interference pattern on the screen. And that's why you get the light, dark with waves. Side note, this is the same kind of technology they use to make wave pools at water parks. What you have is you have constructive and destructive interference. The fun place in the wave pool is to find out where the constructive interference is, because that's where you have the highest highs and the lowest lows. Next time you go to a wave pool, you can also look for and sometimes find the destructive interference zones. That's where, even though you can see really big waves off to either side, where you're standing, the water level doesn't change very much in the wave pool. Okay, so that's waves. What about particles? If you shoot a beam of particles or a stream of particles at a single slit diffraction pattern, particles are going to go through, if again the slit is big enough to be just a little bit bigger than the size of the particles. So think about like paint gun pellets. Think about any kind of small BBs, right? And if those were paint gun pellets, when they go through that slit, the pattern they're going to put on the screen behind the barrier is just going to be a line of paintballs or a line of paint splatters. But it's not going to be any bigger than the slit, because particles don't diffract around edges. And it's going to be a linear path from the slit to the screen. If you do the same thing with a double slit experiment with particles, again, since you don't get interference with particles like you do with waves, and particles can't overlap in space, what you're going to get is two bands of particles on the screen. And so rather than with the waves where we got light, dark, we're just going to get two solid bands where the particles are going to hit the screen. Quick side note about nuclear reactions. Nuclear reactions are when nuclei decay, giving off smaller particles and then producing a different nucleus. If you look at the top left of this picture, we have an image of what's called alpha decay. And this is the kind of nuclear decay that was used in the gold foil experiment. You put a nucleus that undergoes alpha decay in a lead box, put a tiny pinhole in the lead box, let those alpha particles bounce around in the lead box until they line themselves up with the pinhole, and you have a stream of alpha particles. There's another type of nuclear decay reaction called a beta decay. Beta decay is when a neutron in a nucleus turns into a proton. And since neutrons are ever so slightly heavier than protons, an electron in the form of a beta particle is given off. A beta particle is just a high energy electron. If you put a beta decay nucleus in a lead box with a pinhole, you can create for yourself an electron particle gun. Why might we want to do that? Well, you can use your electron particle gun to run a slit experiment. And when you run a electron particle gun through a single slit experiment, you get on the screen exactly what you would expect. Again, these are radioactive particles. If we paint our screen with fluorescent paint, we can see exactly where those electrons hit, and where those electrons hit represents a standard particle single slit diffraction. One single line of particles roughly the same size as the slit in the partition. So what do we want to do next? Well, we're going to run electrons through a double slit experiment. And when we do that, some crazy things start happening. Electrons demonstrate an interference pattern on the screen when you run a double slit experiment. You get a band of light, dark, light, dark, light, dark. Electrons are interfering with one another. And so you might think, oh, well, we can explain that. If an electron goes through the slit on the right and an electron goes through a slit on the left, electrons are both negatively charged. Negative charges repel. It's that charge that's causing the interference. And so they're just deflecting into those positions. Possible explanation. So how do you test that? Well, you can actually get radioactive decay particles that emit beta particles so slowly that you can actually shoot electrons one at a time through this double slit experiment. And we've actually done this, and this represents some time-lapse photography of that. And so over there in B is each individual electron. You can actually see them hitting one at a time, and then they continue, and then D, and then E. And so you see by the time you get to E and enough electrons, you see that light, dark, light, dark, light, dark pattern on the fluorescent screen. So what the heck is going on? The electrons are in fact interfering with each other, but they're, well, not interfering with each other. As the electron is going through this double slit experiment, it's interfering with itself. If you shoot one electron at a time at a double slit experiment, you get an interference pattern. The only way an electron can interfere with itself going through a double slit experiment is if the particles are going through both sides at the same time. Whoa, 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 whoa. That seems like a crazy thing to suggest. An electron would be going through both slits at the same time. Well, there's a way to test that, because scientists who originally ran this experiment said that's absurd. A particle can't be in two places at once. It doesn't spread out. It has particular positions. So what we're going to do is set up an electron detector. Pretty easy thing to do. You put two loops of wires connected to a voltmeter. When a charged particle goes through there, it's going to create a voltage increase, and you can measure which side it went on, because the electron can't be going through both sides. It's got to go through one side or the other. So they set up the electron detector, they turn their electron particle gun on, and sure enough, they got a particle distribution. The electron decided to go through one side or the other, and after a stream of electrons went through, we got 2 bars. So an electron's a particle, everything's fine, except then they took the detectors off, and it went back to behaving like a wave. Electrons cannot seem to decide whether they want to be waves or particles, and this is a fundamental problem in a universe that believes in classical physics, and that things either have to be waves or particles. And this is why we made our move to the quantum mechanical model, because we need to have an explanation of this wave-particle duality within an electron. And so the quantum mechanical model and electron orbitals, which we'll discuss a little more in the next video, are an attempt to explain why electrons behave the way they do. And so one of the reasons we cannot commit to perfect round orbits of electrons around a nucleus is electrons aren't even always behaving like particles. Sometimes they spread out and create energy fields around the nucleus, and they behave more like a wave than they do like a particle. And this is the fundamental issue of wave-particle duality, which we'll explore as we continue through these videos.